Hey everybody, welcome back to chemistry. And so we're moving into some calculations and we're going to go over something called the mole. And so let's jump right into it. So there is a mole in biology, but unfortunately the mole in chemistry is a little different. So a mole, or more precisely 1 mole, is defined as 6.022 times 10 to the 23 atoms or molecules, which seems kind of odd. You know, why did they pick that number and why do they call it a mole? We'll talk a little bit more about that in a second, but for now, you should know that that number, 6.022 times 10 to the 23, is called Avogadro's number, which is symbolized by a capital N with a little capital A. And also, remember that 1 mole of anything is 6.022 times 10 to the 23 of that anything. So why do they call this a mole? So we'll talk again a little bit more about this, but I guess the way I sort of relate to this at this point is I think back to the time when I was a little kid and I first heard the word dozen. I was like, what? You know, what's a dozen? And then my parents told me, well, it's 12 or something. And so I just sort of accepted it. At first it didn't make a lot of sense to me, but then I just kind of came to accept that 1 dozen is 12 of anything. And so I'm hoping that you can sort of accept at this point that 1 mole is 6.022 times 10 to the 23 of anything. But usually in chemistry, it is used to describe that number of atoms and molecules. Okay, so let me give you some examples of moles. First in chemistry. So 1 mole of carbon atoms is going to be 6.022 times 10 to the 23 carbon atoms. Pretty simple. And then if you have 1 mole of oxygen, I'm going to call it molecular oxygen. You can call it diatomic oxygen. This is oxygen in the air. 1 mole of that is that same number, 6.022 times 10 to the 23 molecules. And so 1 mole sulfur, sulfur particles are 8 atoms stuck together. So 1 mole of sulfur molecules is 6.022 times 10 to the 23 molecules. And then other molecules like chloroform or aluminum sulfate, moles of those is that number again. So we can, again, when I was telling you that 1 mole of anything is 6.022 times 10 to the 23 of that anything. So for example, 1 mole of eggs is 6.022 times 10 to the 23 eggs. 1 mole of cars is 6.022 times 10 to the 23 cars. So I'm hoping, and we'll get practical with this in just a minute, is that you can sort of write relationships between mole and 6.022 times 10 to the 23 in some fractions to help you solve problems. And I'll get to that right now. So the first problem I want to address on the board is how many atoms are there in 2.45 moles of copper? Okay, so let's say you have 2.45 moles, and so I guess the abbreviation for mole is MOL, copper. And you want to try to figure out how many atoms there are. Okay, so here, just remember that 1 mole of copper is equal to 6.022 times 10 to the 23 copper atoms. So this is an equality you can use in the problem. So you can set up 2 fractions in your mind, but let me just pick the one that I think is probably going to fit. So I want here moles in the numerator to cancel out with moles in the denominator here. So it's going to be times 6.022 times 10 to the 23 copper atoms over 1 mole of copper. So what you can see is moles cancel out. And if you take 2.45 times 6.022 times 10 to the 23, that should give you the number of atoms in 2.45 moles of copper. So let me work that out really quick. So it's 2.45. And I get on the calculator, it's going to be 1.47539 times 10 to the 24 atoms of copper, but you'll round that to the correct number of significant figures. There's 3 here, there are 4 there. This is not an exact number, Avogadro's number. Here we have it to 4 significant figures. And so what we want to do is round this to 3 significant figures. So it should be 1.48 times 10 to the 24 atoms of copper. Okay, so let's move on to another one. Problem 2. Okay, 2. A silver ring contains 1.1 times 10 to the 22 silver atoms. How many moles of silver are in that ring? Okay, so kind of a similar problem where we use Avogadro's number. So we start out with 1.1 times 10 to the 22 silver atoms. And this time we're going to get it into moles of silver. And again, pretty much the same thing. So can you set up a fraction to solve the problem? So I'm going to go ahead and put in a fraction where there's an equivalency between 1 mole and 6.022 times 10 to the 23. So it looks like I'm going to use times 1 mole of silver over 6.022 times 10 to the 23 atoms of silver. And so you can see atoms of silver cancel out, you get an answer in moles. So this looks like a pretty simple calculation. You just take 1.1 times 10 to the 22 times 1, divide by 6.022 times 10 to the 23, and you should get the answer, and you should be able to round that to, I guess, looks like 2 significant figures. So let's move on. Okay, so the next thing I want to talk about is a concept called molar mass. And so I need to talk a little bit about this. So one question you might rightfully ask is, why is it that 1 mole was chosen to be that odd number of 6.022 times 10 to the 23? And there is a reason for that. And the reason is, if you have 6.022 times 23 atoms of any element, that mass that you have will be exactly the same number as the average atomic mass of the element in AMU. So let me give you an example of that. So let's say you have 6.022 times 10 to the 23 carbon atoms. Well, you now know that's 1 mole of carbon atoms. Again, when you have 1 mole of carbon atoms, which is that number of carbon atoms, then the mass of carbon atoms you have is the same number as the average atomic mass that you see in the periodic table for carbon. So that 1 mole of carbon should have 12.011 grams, because that is the average atomic mass of carbon in the periodic table. Another example would be copper. So when you have 1 mole of copper, you definitely have 6.022 times 10 to the 23 copper atoms, but that amount of copper atoms will weigh the mass. That is the number that you see for the average atomic mass of copper, which in this case is 63.546. So 1 mole of copper atoms will weigh 63.55 grams. Okay, so these gram masses in blue are called molar mass. Okay, so let me give you some more examples of molar masses. So for example, we just went over one example. 1 mole of carbon atoms is going to be 12.01 grams of carbon atoms, because again, the atomic weight of carbon is 12.011. 1 mole of copper atoms is going to be 63.55 grams of copper atoms, because the weight is 63.546. 1 mole of sodium atoms is that number that you see for the average atomic mass of sodium, also known as the atomic weight, 22.99. And same thing with silver. So let's go ahead and do some problems using these numbers. So how many moles are in 62.5 grams of sodium? Let me look up the atomic mass of sodium, 22.99. Okay, so let's do problem 3. So if we have 62.5 grams of sodium, and we want to get this into moles, what you have to do is look up the average atomic mass of sodium. And we just saw in the previous slide is 22.990 AMU. When we see that number, we tell ourselves that that means that if you have 1 mole of sodium, it will have a mass of 22.990 grams. So we can write that out. 1 mole of sodium will have a mass of 22.990 grams. And so you can figure out an appropriate fraction to use. So I'll just go ahead and work that out. So it's going to be times 1 mole of sodium over 22.990 grams of sodium. So grams of sodium cancel, and so we should get an answer in moles. So let me quickly work this out on my calculator. So it's going to be 62.5 divided by 22.99, and I get 2.71825 or 57, and on and on. So let's just round this to the appropriate number of significant figures. And so there are 3 here, it looks like there are 5 here, so we'll round this to 3 significant figures. So the answer should be 2.72 moles of sodium. Okay, let's move on to the next problem. Okay, so how many grams in 2 moles of silver? So let me quickly look up the average atomic mass of silver here. So it looks like it's 107.87. Okay, so how many grams in 2.00 moles of silver? So this is problem 4. So we have 2.00 moles of silver, and we're trying to get this into grams of silver. Okay, so again, you can look up the average atomic mass for silver in the periodic table. It's 107.87 grams per mole. So 1 mole is equal to 187, 107.87. 107.87 grams. So this is for silver. Okay, and so plugging this in is times 107.87 grams silver over 1 mole of silver. And so moles of silver should cancel out. 2 times 107.87 should give you the answer in grams. And so you should be able to round that, I guess, to what? 3 significant figures. And so, as shown in the screen, it should be 216 grams. Okay, let's move on. Okay, so you're going to have to do a number of conversions using these relationships, which include Avogadro's number and molar mass. So one of the things that you should remind yourself of when you encounter these problems, it's always a good idea to convert, say, if you have a mass of an element to moles of an element, because moles of an element can take you to a lot of different places, including number of atoms for that element would be an example, and other places you'll learn about later. So always remember, if in doubt, just convert to moles. That is a really useful rule. So for example, let's say you're given a mass of copper in grams. And so what you want to do is maybe convert that all the way to the number of copper atoms. So a good thing to do is to convert grams of copper to moles of copper. And then once you've done that, convert moles of copper to the number of copper atoms. So you're going to need a few tools to make these conversions. So you already know about the gram to mole relationship, which is called molar mass. And so you now know the mole to actual number of atoms or molecules. It would be atoms in the case of element. This is called Avogadro's number. If you need to convert grams and mils, you can use density. Say if you're converting from grams to kilograms or some other prefix like micrograms or nanograms, you would take advantage of the prefix meeting. So what I want to do is kind of go over this on the light board. Okay, here's the basic idea. So think of moles of an element as sort of being in the center of this universe of conversions. Okay, so one thing you can do, for example, out from moles, you can go to atoms of the element. And so to convert from moles to atoms of the element, or atoms of the element to moles of the element, then what is useful to know is that 1 mole of that element is going to be 6.022 times 10 to the 23 atoms of that element. Now, from moles, you can go to grams. And grams back to moles. And here, you'll have to look up what the atomic weight of that element is. And whatever that number is, that is the number of grams of 1 mole of that element. So that would be the molar mass of the element. So here, I'm just going to write molar mass of element. Okay. So you may not necessarily be at grams for some reason. For example, a lot of times a problem you'll be dealing with volumes, and so maybe you're given some kind of volume. Let's say the volume is in milliliters, but it may not necessarily be in that. It could be in liters, for example, or some other volume unit. And so what you can do is convert volume to mass or mass back to volume using density, because that will tell you the number of grams per milliliter or per liter, for example, for that liquid. So that's a possible thing you might have to do. And another possibility is you may be given a mass, but it won't be in grams. It'll have some prefix. It'll have some kind of like something like kilo. It'll be like kilograms or micrograms or nanograms or something like that. So if you have some kind of prefix, for example, kilo or micro, those are just a couple examples, you will have to convert them to grams with that knowledge of the conversion between the prefix and the grams. So let's go ahead and do a couple of problems with this information. Okay, so first off, how many atoms are there in 34.9 grams of copper? Okay, so we have 34.9 grams of copper. And what we want to do is we want to get this into atoms of copper. Okay, so I do not know of a conversion directly from grams to atoms. So what I will do is first convert grams of copper to moles of copper using the molar mass of copper, and then from moles of copper to atoms of copper using Avogadro's number. So I have to quickly remind myself what the molar mass of copper is. Let me just flip to this really quick. It is 63.546 is the atomic weight. So what I'm going to do here is times 1 mole of copper over 63.546 grams of copper. Okay, again, this will be the number you see in the periodic table, which is the average atomic mass of copper. Now we have an answer here at moles of copper, and so now we want to convert this into atoms of copper. So we use Avogadro's number, 6.022 times 10 to the 23 atoms of copper over 1 mole of copper. And so moles of copper cancel out, and so now you should have an answer to atoms of copper. So what is the math? So the math is 34.9 times 6.022 times 10 to the 23 divided by 63.546. So if you do the math and you round to the correct significant figures, you should get the answer that you see, which is 3.31 times 10 to the 23 copper atoms. Okay, so we're going to move on. Okay, so how many grams are there in 2.2 times 10 to the 24 atoms of carbon? So we have 2.2 times 10 to the 24 atoms of carbon, and we're trying to get this now into grams of carbon. So this is kind of a similar problem, except you're working backwards. So this time you convert atoms of carbon to moles of carbon using Avogadro's number, and then moles of carbon to grams of carbon using the molar mass. So I'm just going to fit those in. So it's going to be 1 mole carbon over 6.022 times 10 to the 23 atoms of carbon. Atoms of carbon cancel. Now you have an answer in moles. And so now we got to get moles of carbon to grams of carbon. So here we remind ourselves what the average atomic mass of carbon is. And you can look it up in the periodic table, but it's 12.011 grams per mole. So it's times 12.011 grams over 1 mole. And so 1 mole cancels. And so the math should be 2.2 times 10 to the 24 times 1 times 12.011 divided by 6.022 times 10 to the 23. And that should give you the mass of carbon, and then just work that out to the correct number of significant figures. Let's move on to the next problem. Okay. The next problem reads, what is the mass of 1.00 times 10 to the 6 atoms of iron in nanograms? Okay. So a little bit trickier. So we have 1.00 times 10 to the 6 atoms of iron, and we're going to have to get this eventually into nanograms of iron. Okay, so what I would do first is just, if you have something in atoms of an element, just convert it to moles of the element. That's the easiest thing to do. So it's times 1 mole of iron over 6.022 times 10 to the 23 moles of iron. So the moles, or excuse me, mistake. Come on, brain. Atoms of iron. Okay, so the atoms of iron cancel out and you get an answer in moles of iron. Okay, and so now we want to take this to the mass of iron. So we need to know the average atomic mass of iron, which is 55.845. And so that means that 1 mole of iron will have 55.845 grams in it. So let me just carry this down here. So here I have times 55.845 grams of iron over 1 mole of iron. And so you can see moles of iron cancel out and get an answer in grams. But the problem is we want the answer in nanograms. And so what would be useful here is knowing the relationship between nanograms and grams. And so what I remember is that in 1 nanogram, there is 1 times 10 to the negative 9 grams. So grams of iron should cancel, and we should get an answer in nanograms of iron. So if you work that out, 1.00 times 10 to the 6 times 1 times 55.845 times 1 divided by 6.022 times 10 to the 23 divided by 1 times 10 to the negative 9, you should get that answer on the screen. So let's work on the next one. So the density of mercury is 13.5 grams per mil. How many atoms are there in 2 mils of mercury? Okay, that's a good problem. So let's say you have 2.00 mils of mercury. And what we're trying to do is we're going to try to get this into atoms of mercury. So down here, we're going to be at atoms of mercury. So I don't know a conversion between milliliters of mercury and atoms of mercury. So let me tell you about how I think about this problem. So maybe right before atoms of mercury, I probably would have moles of mercury, right? Because then I can use Avogadro's number to take moles of mercury to atoms of mercury. So what would I have before moles of mercury? Possibly mass of mercury, right, in grams. Now the problem is we start out with a volume of mercury. So the question is, do we have density of mercury in the problem? Yes, we do. We know the density of mercury is 13.5 grams per mil. So we should be able to take this volume of mercury in mils and just convert it to grams of mercury, and then using the molar mass, get that to moles of mercury, and then from moles of mercury to atoms of mercury using Avogadro's number. So let's go ahead and do that. So it's going to be 13.5 grams of mercury per mil. So that's an equality. That is 13.5 grams of mercury is equal to 1 milliliter of mercury. So I can go ahead and write out the fraction here times 13.5 grams of mercury over 1 milliliter of mercury. And the milliliters of mercury cancels out, and at this point we have an answer in grams of mercury. And so what would be the next step is probably just to convert this to moles mercury using the molar mass. And so the average atomic mass of mercury is 200.59 AMUs, which means if you have 1 mole of mercury, it's going to weigh 200.59 grams. So I'm going to write that in here. So 1 mole mercury over 200.599 grams of mercury. So grams of mercury cancel and you get an answer in moles of mercury. And so the final step is just take the moles of mercury and just convert that into atoms of mercury. So it's going to be times 6.022 times 10 to the 23 atoms of mercury over 1 mole of mercury. And so moles of mercury should cancel out, and now you should have an answer in atoms of mercury. So what would be the answer? It would be 2.00 times 13.5 times 1 times 6.022 times 10 to the 23 divided by 1 divided by 200.59 divided by 1. So if you do the math, you should get that answer that you see on the screen, 8.11 times 10 to the 22 atoms of mercury. And that seems to be rounded to the correct number of significant figures. Thank you for listening. We'll see you next time.